Welcome back. In this video we'll be building a circuit that I refer to as a single transistor and paper water leak detector. The inspiration for this circuit is it's basically just a single transistor touch switch setup, but when the switch is touched, a Piezo buzzer goes off. And how does the touch occur? Through a piece of paper with some wires. I'm using jumper wires for this demonstration, but just it's easier to show what it does than necessarily describe it in great detail. You have our 6 volts of battery, have our dish to catch the water, and normally you want electricity and water to stay as far away as possible from each other, but in this case this is exactly what you want. Imagine you have a plastic dish sitting under your sink, and you have this circuit wired up. It sure would be nice to know that you have a small leak under your sink before you step in the water in the middle of the night, like I did the other night. And it had been leaking for a while, but it took quite a while for that water to come out from the cabinet to the floor, and by then it's wet all of your cabinets, and you have moisture under them, then you have to be worried about mold, etc., etc. Whereas this simple little circuit, costs next to nothing to build, is so helpful in that regard. You have your paper and your dish under your sink trap or wherever you think you may have a water leak one day, and all that has to happen is this is water supposedly purified, and just a little bit. It hits the paper, no problem, no worries. As soon as there's enough water, it goes off. And we have a warning before our pan is completely saturated. And all that's happening is the water is creating a path for the electricity to flow through these wires. We have one wire in our voltage rail, and it's serving as a way to send voltage and current to the base of the single transistor, which is in turn turning on our piezo element. So this is the same principle as a touch switch, where you could have these two wires and you could touch both of them together. Then you could create a sound. And everybody knows if you lick your finger just a little bit, you get more of a light, more of the light. Normally there's a light hooked in here, and the more you wet your finger, the brighter the light will be. Well, in this case, the wetter you make your finger, the louder the piezo will sound. And in this context, we're using a piece of paper between two wires that as soon as it gets wet, that's just like a wet finger touching these two contacts, in turn sending power to the base of the single transistor, which sends power to the piezo buzzer and alerting us, oh, we have a water leak. And with my experience, I tried the water coming out of my faucet and supposedly purified water, and there is enough particulate in purified water to turn this on, so most anything coming out of one sink will turn it on. It does not have to be salt water by any means to create a good continuous connection between the two clips. So it's a simple water leak detector. It's really cheap to build. It's a really useful circuit. If you're like me and don't want to wake up in the middle of the night stepping in water from a leak that's been going on for however long, week, month, who knows. And this sort of circuit will solve that problem for you. The schematic for this circuit is very simple. We have our voltage going to a clip with our piece of paper in between to another clip. And the paper has more than enough resistance to keep any voltage or current flowing across. I'm just using, in this demonstration, very tiny pieces of paper. Most any size paper would work. You could use an entire sheet. This is just standard printer paper. But you could use multiple types of paper, and you could use larger, longer pieces, shorter pieces, whatever you think you need. The larger you make the paper, the longer it may take for the water to reach the edges and in turn turning on the buzzer. So the smaller you can make it, in a sense, the better, but a larger sheet of paper would catch the leak in a sense, quicker, especially if you have it in a pan under your sink. Not all of us are fortunate enough to have sinks that don't leak from time to time. So the way it works is when the paper is dry, there is no voltage or current crossing that paper. But as soon as it's wet, that sends the voltage and the current through this 1K current limiting resistor to the base of an NPN. I'm using a 2N2222 standard NPN transistor, as generic as a 3904. A 3904 would work with this too, an NPN 3904. And it sends current. Once the paper's wet, enough current is sent to the base. In this case, I'm using 6 volts. So you have 6 volts. The base of the transistor is going to drop 0.7 volts. So you have around 5.3 volts going to the base of the transistor. With that current limiting resistor, you're looking at 5.3 milliamps of current, which is more than enough to turn on an NPN 2N2222. And these transistors typically have a gain of 100. So that means if you got 5 milliamps here, in principle, you could get 500 milliamps of current flowing through this if you needed it. But the piezo that this transistor is driving, the one I bought, only requires 10 milliamps of current. And as most have figured out if they've been in the electronics world for a while, is that how much current is actually going to be drawn? Well, as much as the piezo needs to run. So really this is an overkill transistor. You could use the 3904 and still have plenty of overhead to drive a piezo at 10 milliamps or 30 milliamps or 50 milliamps. Whatever it happens to be. I'll put the part numbers to the particular piezo buzzer I used in the description. So what happens is the transistor is turned on when the paper is wet, creating a path for the current to flow. It flows through the piezo, sounding the alarm. Then, well, what happens when we disconnect it? That's where this diode and resistor come in. As the piezo does generate a certain amount of inductance, and we'd rather that inductance go around the piezo, just like with a relay, and let it dissipate, rather than happen to go through our transistor and blow it out. So the diode's just a flyback diode in reverse bias, meaning that it's pointed toward the positive rail. Its cathode side is, so no voltage or current will flow this way. It'll stop at this point in the diode, but it allows the inductance of the piezo, when it shuts off, when we disconnect the circuit, to spin itself out in this loop rather than going down and blowing the transistor out. And with this 1K resistor right ahead of the diode, this will actually have voltage to this point, which will help slow that inductive kickback as the piezo powers down. And that's all there is to this circuit. A really simple circuit, simple parts, easy to build. This is the standard circle translation sort of diagram, but we're going to build it on a breadboard, so it's always nice to have a more breadboard laid out circuit. So we'll be using this particular schematic as we build the circuit. It's the exact same as the previous one. It just is easier and follows the breadboard. The only thing one has to be careful of is these NPN, these 2N2222 transistors. Their pinouts are not always the same, so you'll need to check to identify what is my collector, what is my emitter. And that's easy to do with a multimeter. Put your multimeter in diode mode. Put your red lead to the base of an NPN style transistor, and take your black lead, touch one leg, write your reading down. Touch the other leg, write the reading down. Whichever of the two legs gives you the higher reading, that's your emitter, given the way NPN transistors are doped on the inside. The higher reading will be your emitter, the lower reading will be your collector. If people are a little confused about how to do that test, I can do a video. The other people have done them on YouTube, how to determine the collector and emitter and base of an NPN or a PNP transistor. You can look that up or just let me know in the comments. I'll be glad to do a video on it. But that's really the only tricky aspect, if there is any tricky aspect, to this real simple circuit. is just getting your collector and emitter right. And the circuit will still oftentimes run if you get these backwards, but it'll get hot normally, and it's not running current or through the proper direction of the transistor. But this is the orientation of the transistor I had. The curved side was to the back, and this is the way the pinout would work when the curved side's to this direction, the flat side's to this direction on a breadboard. Let's build this circuit. The first thing we'll need is just a breadboard. I've connected the power rail all the way down this side of the breadboard and the ground rail all the way down this side, given the way I'm going to plug in the battery pack. We have our breadboard, and we can look to our schematic. The first thing we need, we can start at the top of the VCC, which is 6 volts in our case. The particular piezo I'm using says it would be fine from 3 volts up to almost 20. I'll have to look at the package, but yeah, 3 to 20 volts DC. There's the part number if people need that. I'll also put that in the description though. But the first thing we need is just a wire from VCC into the rows of the breadboard, giving us 6 volts once we plug our battery pack into that rail of the breadboard. The next part we need is a 1K resistor and the diode in reverse bias. This is a 1N4148 diode, just a small switching diode. It's a 1K resistor and our diode with these small 1N4148 diodes. The black line is the cathode. We want it in reverse bias, so we point it back toward VCC, this line. Then next we need our piezo buzzer with the red wire going to VCC ahead of that 1K resistor and the diode. I've just soldered some ends on this buzzer just to make it easier to plug into the breadboard, and we'll put it right ahead of our 1K. That's all we've done, and we've put that diode, and this diode's in the same row as the leg of that 1K resistor, and there is the red wire to our buzzer. Then the black wire of our buzzer comes in and runs into the bottom of our diode, the leg of our diode. Black wire runs in to the bottom leg of our diode. Then our 2N2222 NPN transistor, we need the wire coming from our piezo and our diode. The row in the breadboard needs to go to the collector of our transistor, and the curved side, as long as we put it to this direction, will be in good shape. There's the flat side, there's the curved side, there's the collector pin. It needs to go in the same row as the bottom leg of the diode, as well as the bottom black wire of our piezo. Then we need a 1K resistor from the base of our NPN transistor out to a clip, but first let's just put in the 1K. 1K resistor, and we'll just leave it out. We can hook our clip onto that for demonstration purposes. And there's our middle leg of our transistor, the row that it's in. The 1K resistor is in that row. This is for the base to turn the transistor on and off. And one of our clips will need to go to it, so no problem. Just add a clip onto it. And the bottom leg of our transistor, the emitter, needs to go to ground. I need another little piece of wire to get all the way to ground. There we go. The emitter of our NPN transistor is going to the ground rail on this side of the breadboard. Then we'll need our piece of paper and a clip going to VCC, or 6 volts. So here's VCC, 6 volts. We can just add a wire for demonstration purposes. It's in the 6 volt power rail. Hook our clip on to it. And then all that remains, we can zoom out, is to put a dry piece of paper between the 2 clips. You can orient them however you want. You can make your own jumper wires like this, buying some of these ends, or you can use some of these cheaper jumper wires. I got 5 or 6 in a package from somewhere like Harbor Freight. Then all we have to do is add our battery pack and switch it on. And you can test to see, is the circuit functional. And in order to do that, all you have to do is touch these 2 ends together. We can use a piece of wire to do that. And if your piezo buzzer sounds, you know you've done it right. And can do a proof of concept test again. We have our plastic dish. We could set this under our sink and we wait for the leak. Fortunately, we can make our own leak, and we have those drips, and it soaks into the paper. And notice the length to the paper will determine how long it takes for continuity to form between those 2 clips. Whoop, that's enough. And that's all there is to the circuit. And it'll work every time. It's reliable. And when the beauty of this is, when the paper is dry, you can take your multimeter and put it into your current draw, and there is no current draw from this circuit. So the batteries, these 4 batteries, will last just like they're in a package sitting in your drawer. So you don't have to worry about your batteries will last as long with it switched on, about as long as, transistors have a little bit of current leakage oftentimes, but you'll get a long life out of these sort of AA style batteries. These batteries should last almost as long as they would in the drawer. And so you don't have to worry about it. You just need to check them from time to time. Take your voltmeter, see how much voltage is coming out of them. Make sure there's still plenty of voltage to sound off your piezo and trip the base of the transistor. And that's no more nor less to the circuit, and it's a useful little circuit. I know that I will put it on proto board and have some clips with a piece of paper under my sink from now on with a little plastic dish, because it's certainly not pleasant to wake up and have water in your floor. I hope this video has been helpful. If so, please consider clicking like, and then also consider subscribing to my channel. Until next time.